good morning to all of you. So, today we will continue the discussion to another very important distribution in statistical mechanics, which is called as the binomial distribution. So, we will be focusing our attention to binomial distribution, and I will give you an example where, in fact, there are several examples where this distribution is applicable, and I will discuss towards the end of this lecture a very important example for binomial distribution, which is a random walk, and to that end we will be discussing a random walk in one dimension, because that is the simplest case which has all the features of a random walk except that it is the easiest to handle. So, we will discuss the one dimensional random walk as an example of the binomial distribution. Okay. Right. So, let us define what is a binomial distribution. Now, the word bi here signifies that you have two outcomes. Okay. So, I am interested in events which have two outcomes only, okay, or interested in let me use a more accurate word, interested in observations that have only two outcomes. Let us say, let us pick the example of a coin toss. Okay. So, I am going to underline it because that is an important criterion for a binomial distribution, only two outcomes. Okay. If there are more than two outcomes, then you have a multinomial distribution, but that is not the subject matter of this lecture. We are only interested in events or observations where the outcome can only be two, one of the two. So, let us say the outcomes are A or B. A or B here could refer head or tails in a coin toss. Now, associated with these events, there are probabilities which I am going to call as, so the probability of getting an A are P A and P B. So, if I toss a coin which is unbiased, then the probability of getting a head, let us say, is P of A, then the probability of getting a tail is P of B. Now, since there are only two outcomes for a coin toss, I can say that the probability of getting B is 1 minus P of A, because the probabilities have to be well behaved, okay, because I want the probabilities to be well behaved. So, this is like a conservation of norm for the probability. Okay. Now, let us continue the example of a coin toss. So, if I toss a coin n times, okay, so let us say toss a coin n times. This is like in the language of StatMech, we are doing an experiment n times. Each time we get an observation, okay. And suppose you are interested in the probability of a particular realization where in n tosses you saw the heads n times, okay. So, the probability of getting n occurrences of the event A, is given as, I am going to call it as P of n A. So, the probability of getting the occurrence A NA number of times in a total of n tosses or n experiments is given as where you had NA times the event A and the probability of each event is PA. So, but you got it NA times, so it has to be raised to the power of A. Okay. These are independent events, and naturally when you had A occurring NA times, you had the B occurring NB times, which is n minus NA. Okay. So, the probability is n minus NA, PB raised to n minus NA times PA n raised to NA. But as you can see, so this would be, for example, I am going to pick a very simple example. So, you let us take n to be 5, okay, and you say that I have tossed the coin n times 5 times and I got the heads 3 times and I got the tails 2 times. Okay. So, what is the probability of getting 3 heads and 2 tails if I toss it 5 times? Well, you can say that the toss probability is P of A, which is 1.5, I know it is 1.5 raised to the power 3, and I need to, for each time, I mean out of a total 5, if there were 3 heads, there were also 2 tails. So, the probability of 3 heads and 2 tails, the joint probability is PB to the power 5 minus 3, which is 2. Okay. And let me draw one realization of this. So, I got a heads, a heads, a heads, and I got a tail twice. Okay. But then you can also have a head, tail, then a head, tail, then a head. Okay. You could also have heads, then 2 tails, and then 2 heads, and so on. So, what you have written here is basically the probability of one ordering, but I know there are several orderings, and precisely the number of orderings is known to me, which is 5C2 or 5C3. So, definitely I must multiply this probability, which is for a single occurrence, with the number of orderings I can have. So, I need to multiply it with 5C3. It is also okay if I multiply with 5C2, because the binomial combination is symmetric in its 2 variables. The fact is, this probability that I have written here is for a single ordering, and one has to account for all the orderings possible, and precisely for that I am going to multiply it with NCNA. This is a abbreviation used for the combinations I can get. So, this stands for n factorial upon NA factorial into n minus NA factorial. Okay. So, this factor here that I have written as a combination is the number of orderings you can write down for NA outcomes and NB outcomes. Okay. What I have written here as a probability is a probability of a single outcome or a single ordering. Okay. And the multiplication factor here is the total number of orderings that you can, this is the total orderings you can have for a given number of A outcomes. Okay. So, that is the meaning of binomial probability. Fine. So, now I want to develop some very important mathematics here that will greatly simplify your task for computing moments and cumulants of a binomial distribution, and this is going to be very important when you apply binomial distribution to problems in random walks that are profound in statistical mechanics. Okay. So, clearly with that goal in mind, I am going to build some very interesting mathematics here that will help you apply the concepts of a binomial distribution to problems in random walks. Okay. So, let me straight away construct the generator of moments, which we call it as the by this lecture you already know that the generator of moments in our course is the characteristic function. Okay. So, I am going to construct the characteristic function as the simple Fourier transform of my probability distribution, which is the binomial distribution. Now, this is a distribution which has a discrete number of outcomes. The random variable NA is discrete. So, I have to take a discrete Fourier transform here. Okay. So, let us do that. So, the Fourier transform of our PDF is now P of k out of n trials. So, this is a characteristic function that I am interested after n trials, okay, or n measurements or n experiments. So, this is given as nothing but the discrete Fourier transform. The integration variable or the summand variable is now n a, okay, and this will run from 0, okay, because that is the lowest value for a. You cannot have less than 0. 0 is the minimum value n a can take. So, this would be like saying all outcomes are b, okay, and the maximum value for n a has to be n. It is like saying all outcomes of the n measurements were a. So, n a will go from 0 to n, okay, e to the power minus I k n a, because n a is my integration or summand variable, times my binomial distribution, which is p of a to the power n a, p of b to the power n minus n b n a, into the combination n c n a. Okay. Now, let us club these two factors together, exponential NPA, and you shall see that this begins to look like a formula that you know already. So, e raised to minus I k into p of a are clubbed together and they are raised to a common power n a times p b to the power n minus n a times the combination n c n a. And as I said, this is a well known expansion of the sum p a plus p b. Okay. So, this is a binomial expansion of the sum of e to the power minus I k into p a plus p b raised to the power n. Okay. So, this is the binomial expansion okay, that we know from elementary mathematics. Fine. So, you now have a characteristic function ready and you can do a lot of things with it. So, for example, you can now straight away go and compute the moments of binomial moments of the random variable n a. You can also compute the cumulants, the first cumulant being the mean itself, the second cumulant being the variance of the random variable, the third cumulant being the skewness of the random variable, and the fourth moment being the kurtosis of the random variable. All these cumulants and the moments can be computed once you have the characteristic function. So, before we delve into all that, let us box this important result and then we will proceed towards computation of the cumulant generator function. Okay. So, this is my characteristic function ready for use. Okay. So, you can compute the cumulant generating function by simply taking a logarithm of this. Okay. So, the cumulant generating function can be computed by just taking a logarithm of the moment generating function or the characteristic function, which is nothing but n times, if you take the logarithm of ln e raised to minus I k p of a plus p of b. Okay. So, you have now the cumulant generating function also available with you. You can do a lot of interesting stuff with this. Okay. So, now you have a very powerful handle to compute moments of the random variable. In fact, actually do a very interesting physics problem, which is the random walk problem. Okay. So, we will take up a random walk problem shortly and demonstrate the use of these powerful formulas. Okay. So, I just want to mention something here, that if you look at your characteristic function, it is very easy that if you want to compute the, let us say, the mean of NA. Okay. So, for example, if you toss a coin n times and you want to know how many times, what is the average number of heads that you can get, well, the answer is straight away in front of you, because if you take you know that this coin has only two sides, heads and tails. So, after n trials you will get approximately half the number of heads, that is known to you, but you can also see that it is straightforward. It is also obtained from your formula here. If you just use the definition of means, well, the average of NA is nothing but the first derivative with respect to I k of your moment generating functions after n trials, and this has to be computed k equal to 0. I am just saying that you can convince yourself that this machinery is working. Okay. You know, for a coin toss this is very simple, but let us just apply this machinery to a very simple problem for a proof of principle. We can take the machinery for more complex problems later. Okay. So, you can just take the derivative and it will become n times e to the power minus I k p of a plus p of b to the power n minus 1, and there is an e raised to minus I k inside, which will give me p a times e raised to minus I k. Okay. And definitely I have to compute this derivative at origin. Okay. So, you can see that this is nothing but, if you put k equals to 0 here, what you get is nothing but n times p a, because p a plus p b is 1, and that is what you want. Okay. So, your average number of heads after n trials is nothing but n times the probability of getting a head in a single toss. Now, if probability of getting a head is half, this would be nothing but n by 2, because the coin is unbiased for an unbiased coin. Okay. So, this this should convince you that this machinery is working and you are not you are getting what you expect. Okay. The answer is expected. Now, we have to take this machinery of moment generating functions to a simple but very important problem in physics, which is the random walk problem, and that will be provided here as a worked example to elucidate the concepts of the preceding discussion. Okay. So, I am going to take the example of a random walk. This would be a worked example which will demonstrate application of the concept in the random walk. Okay. So, I am going to take a random walk in one dimension. Dimension is 1 only for simplicity. Okay. It is not it is easy to discuss everything in one dimension without much difficulty, and it explains the concept. So, you can generalize this to n dimensions without the only difference would be that the calculations will become tedious. Right. So, Let us look at random walk in one dimension. So, let us say you have a, you can always say that a walker, our 1D walker, he is walking on a line. Let us say this line is the x axis, and there is a lamp post here, okay, where he starts his walk. Now, the walker can go right with the probability P of A, and the walker can go left with the probability P of B. Let us say that the walker is unbiased. Naturally, this has to be a drunkard walker. Okay, he has drunk, he has consumed so much alcohol that he does not know where to go. He is unbiased. So, which means he is sufficiently drunk for his probability of forward step and the backward step to be equal. Okay. He is taking steps in the forward direction and the backward direction with equal probability. Now, suppose I ask you a following question: what is the probability? And one more thing, the walker is unbiased and he takes steps of unit size. Okay. Now, this is going to be a very ideal drunkard whose step size is going to be fixed, but let us say that is an approximation I am going to sort of work with. So, he takes steps of unit size. Yeah. Sorry, this is 1/2. It has to be 1/2. Obviously, otherwise it is garbage. So, let me correct immediately myself. Thanks for the correction. There is a typo here. The sum of probabilities has to be 1. So, let me just quickly correct myself. I wanted to write PA plus PB as 1. I ended up writing PA equals PB equals to 1. So, what I mean is basically that the probabilities are equal and they add up to 1, which means they all have to be half. Okay. So, let us underline these two important assumptions, because we are going to use them in our discussion. So, this is one important thing that I have assumed, that the probabilities are equal in the forward and the backward direction and they are half. Another thing that I have assumed is that the steps are of unit size. Okay. These are the two assumptions I am going to work with. Now, the question that I have raised here is, so what is the probability of finding the walker at location x equals to m. Okay. So, what is the probability that the walker after n steps is at location x equals to m? Okay. So, I am going to just write down after n steps. Okay. Question is simple. He has taken a large number of steps, let us say 1000 and or 500 or 10,000 or whatever, and after these many steps, what is the probability that he is at some point m on the x axis? Okay. So, naturally you can tackle this problem by saying that total number of steps is n. Okay. And let us say steps in the forward direction is let us say this is NF, Okay. So, steps in the backward direction actually should be n minus nf, because the steps are, the total number of steps is the big N, and so your net displacement, assuming the walker starts from origin. Okay. So, as I said, the walker starts from the lamp post. Okay. He starts from the lamp post. So, his initial position is the lamp post itself. Let us say the lamp post is at origin, and so the net displacement of this walker, which is our variable m, has to be number of steps that the walker takes in the forward direction minus the number of steps that the walker has taken in the backward direction. Now, this is already computed. So, we know that the backward direction steps are n minus nf, okay, which gives us the value as twice of nf minus n, the big N, fine. So, what is being asked is basically the probability of so the probability that the walker is at the location m after n steps. Okay. So, this is basically nothing but if I take the average value, or no, so what is being asked is basically what is the let me just correct myself. So, what is asked is basically we need to compute the average m. So, what is the okay. So, we are trying to find out the probability of finding the walker at the location x equals to m, fine. So, let us start with that and then we will prove the average m, we will find out the average m, okay. That is also fine. So, this probability of finding the walker at location m, the probability of finding the walker at location m is nothing but the probability of finding the walker who has taken nf forward steps, okay, in n steps, in a total of n steps, because he has taken nf forward steps, naturally he has taken n minus nf backward steps. So, it suffices to just take the probability of nf here, and that would be nothing but as we have already seen, the probability of a forward step to the power nf times the probability of the backward step to the power n minus nf, and the combination which is nc nf, okay. That is the probability of finding the walker at location m with nf forward steps, okay. So, now you can just take the, that is the answer to your first question. Let us take it further. So, taking further, you can compute the characteristic function, which is nothing but the Fourier transform of this distribution, and that, as we have already done, turns out to be p forward to the power e raised to minus I k plus p backward to the power n. Okay. This is the expression here. Okay. So, let us plug the values of forward and backward. We know these are half. So, what you have is basically e raised to minus I k. You can take the half outside plus 1 to the power n into 1 by 2 to the power n. Okay. So, if you plug Pf and Pb as Pf and forward and backward as half, you can take half outside, and what you will get is just e raised to minus I k plus 1 to the power n into half to the power n. Okay. So, you can now compute what are these. So, suppose you are interested now in computing the averages. Okay. Suppose you want to compute okay. So, you want to compute the average displacement, okay, or you want to compute the square of the displacement average, okay, or you want to compute the the average of the cube of the displacement. These are all averages that one might be willing to compute. Then the calculation becomes very simple. So, we know that mod m is nothing but mod of twice nf minus n, okay, because m itself is given here. So, this is your m, let us underline it. So, this is your m. So, if you want to take an average of this is just twice of average nf minus n. Okay. So, this would be just twice of nf minus n, because n is a constant, the big N is a constant. So, average of big N is nothing but n itself. Right. So, now you can also compute m square as twice nf minus n the whole square, which is, if you open the brackets, what you get is basically 4 times nf square minus 4 nf into n plus n square. Okay. And similarly, you can compute the other values for moments, as I am just writing it down from my notes, but you can consult it, but you can compute them on your own and verify that this is correct. Okay. So, let me just write down the values directly, you can compute them by yourself. Okay. So, this is very straightforward. So, I am just directly writing down the result, and for M4 this is 16 nf to the power 4 minus 32 nf cube to n plus 24 nf square mod n square minus 8 nf into n cube plus n to the power 4. Let me just quickly check if everything is right, and then we will proceed forward. Yes. So, this is all correct. Okay. So, these are the expressions for moments. Okay. All the moments are here, and we can compute all these moments very simply. Okay. So, Let us first compute to compute. If you look at the right hand side of all these moments, all that is required is basically just the moments of NF. Okay. So, what the required quantities are just the moments of NF. Okay. All you need is basically these moments and the fourth moment, and that will give you the moments of M. Okay. So, let us compute the moments of n, small nf, and which is nothing but as you already know is okay, and that you already know this is n times p of a, which is n by 2. Okay, this we have already computed, but if you want you can compute again from this expression. So, you already have the value for p n of k, and from here if you want to compute you can compute it directly. Okay, so, you can take the derivative with respect to n and get the answer. So, okay, so that would be the answer for NF. Then you can compute the value for NF square, which would be the second derivative of P of k at origin, and using the value of P of k from the top, okay, you can compute this to be n square by 4 plus n by 4. Okay. Just work it out, and for NF cube you can compute this as the third derivative, and this will come out to be n into n square plus 3 n by 8, and the fourth moment will come out to be n 4 plus 6 n cube plus 3 n square minus 2 n by 16. You have to do this calculation on your own. These are very straightforward calculations, and you will get the answer very easily. So, if you want I can do one or two of them for your help. So, I am going to write down this, let me just copy paste this expression, so that okay. So, this is the expression for the cumulant generating function, the moment generating function. So, from there you can easily see the first derivative comes out to be n times p a. So, let us take the first derivative, which is n f. Okay. So, I am just going to take the derivative of 1 by 2 to the power n e raised to minus I k plus 1 to the power n, and this derivative has to be taken at k equal to 0. So, 1 by 2 to the power n can come out. Okay, so, this is just a constant. What you have inside is just n times e to the power minus I k plus 1 to the power n minus 1, and what you have inside is just e raised to minus I k, that is it, and that is taken at k equals to 0. So, what you have here is at k equal to 0, this simply becomes 1 by 2 to the power n into this becomes 2 raised to n minus 1, because this is 1, this is 1, this is 2, 2 raised to n minus 1, and that is nothing but n by 2. Fine. If you want, we can do one more just to sort of give you an idea. I will do the second cumulant also and leave the third and fourth as assignments. Okay. So, the second cumulant is the second derivative, sorry I keep saying cumulant, this is the second moment of the moment generating function, which I am going to just write from the formula above. So, which is nothing but 1 by 2 to the power n into e raised to minus I k plus 1 to the power n at k equals to 0. So, this 1 half to the power n will come out, and the first derivative is already written in front of you. So, I am going to take the first derivative as is from the top and take one more derivative here. So, this would give me n minus 1 to the power multiplied by e raised to minus I k plus 1 to the power n minus 2 into e raised to minus I k, but there is also an e raised to minus I k outside, plus e raised to minus I k plus 1 to the power n minus 1 into e raised to minus I k, and all this is taken at k equal to 0. Fine. So, this will give you, if you put k equals to 0, what you have outside there remains 1 half to the power n into n. Let us see what happens to the inside. You have n minus 1 into 2 raised to n minus 2 plus 2 raised to n minus 1, that is it, and that becomes if you so this would be, if you take the 2 raised to n inside, if you take 2 raised to n minus, yeah. So, what you do is basically you take 2 raised to n inside. So, what you will have is n minus 1 to the by 4 plus 1 by 2. Okay. So, I am taking the 1 upon 2 raised to n inside. So, this will give me n into n minus 1 plus 2 upon 4, which is n into n plus 1 by 4. Okay. So, that is what we had for the second cumulant, n square plus n by 4, right. So, I am leaving the other two cumulants, other two moments to be calculated by you. It is a straightforward derivative, the only thing is it becomes tedious. So, I am going to leave this as an assignment. Eventually, when you plug all these moments of NF, the forward displacements, into the expressions for M, which is here. Okay. So, let me box this. So, after you find all the moments of NF, you are supposed to plug it here in the right hand side. Okay. And then you will get the values for all these m's. So, you will get all these m's, this second moment, third moment and the fourth moment. Okay. So, the moments of the net displacement are then straightforwardly calculated. So, and this is an important result. So, the first moment of the unbiased random walk has to be 0, it will come out to be 0. The second moment will scale with system size, and that is given as just n. The third moment will also come out to be 0. Okay. All odd moments will come out to be 0. The fourth moment will come out to be 3n square minus 2n. So, this is a very powerful method. So, all moments can thus be calculated. and I am going to argue that they are calculated very easily if you know the techniques of the characteristic functions. Okay. So, this calculation just involves taking the appropriate derivatives of the characteristic function and simply computing the moments from this relationship that we have derived. So, the averages of the net displacement of a random walker which is taking unbiased steps in one dimension are straightforwardly calculated, and this is a direct application of the characteristic functions that we have discussed in our course so far. So, I will end the lecture here, and with next time when we meet we will start off with the discussion on Poisson distribution, which is another very important distribution in statistical mechanics. So, these are the three major distributions, and I will cover some worked examples before you meet your first assignment set in this course. Okay. So, thank you very much. We will close the lecture here.